Tonight, more evidence that the nation's infrastructure is crumbling.
Thanks, Alex. As he mentioned this morning, we are keeping our eyes on Greene County, specifically
beneath the rolling hills and fertile valleys of Tennessee. Something unexpected stirred deep within the earth. The movement was subtle at first, a barely perceptible shift in the dense rock strata that had lain in silence for millions of years. Seismographs and scattered research stations began to pick up irregular patterns, minute changes that hinted at something unusual occurring far below the surface. The data poured in with an unsettling consistency, suggesting not just a tremor or isolated fault slip, but a coordinated movement in the crust, a movement strong enough to set off alarms in geological monitoring centers across the region. Experts knew what they were seeing was not part of the usual seismic background noise. This was different. It was focused, rapid, and large in scope. The kind of activity that speaks of deep tectonic forces suddenly waking from long dormancy. Before we start, smash the like and subscribe buttons for more updates. The Appalachian region is not the first place most would expect such alerts. Known more for its ancient, eroded mountains than for active seismic threats, Tennessee's subsurface is generally thought of as stable compared to places like California or Alaska. Yet history tells a different story for those who know where to look. The New Madrid seismic zone, just to the west in neighboring states, has been the source of some of the largest earthquakes in North American history, including the infamous quakes of 1811 and 1812 that were powerful enough to make the Mississippi River flow backward. Though Tennessee lies partly outside the main zone, the crust beneath it is laced with old, buried faults and fractures, scars from an ancient geological past that still hold the potential for sudden and violent movement. The recent crust shift appears to be linked to one of these hidden fault systems, possibly a deep-lying structure not yet fully mapped. Sensors detected vertical displacement along with lateral shearing, indicating that the rocks were not merely cracking, but being pushed in multiple directions. This kind of multi-directional stress is rare, and often signifies that forces from deep within the mantle are redistributing themselves, pushing against the lithosphere in a way that releases built-up strain all at once. In geological terms, this is like a tightly wound spring snapping free. In human terms, it is a moment where the Earth decides to reconfigure itself in ways we cannot control. What startled geologists the most was not just the occurrence, but the speed at which the event unfolded. Typically, deep crustal adjustments take place over days or weeks, giving some lead time for analysis. This movement, however, accelerated in mere hours, going from background noise to peak displacement with alarming speed. Such rapid deformation suggests either a sudden injection of energy from below, possibly magma or superheated fluids forcing their way upward, or a cascading failure along a fault plane that had been precariously balanced for centuries. Either way, the implications are profound. Fast, deep movements have the potential to redistribute stress over vast areas, setting the stage for further seismic activity that may not remain confined to a single fault. The geological makeup of Tennessee adds another layer of complexity. Beneath the rolling farmland and forested ridges lies a varied and fractured foundation of sedimentary rock, metamorphic zones, and occasional igneous intrusions from ancient volcanic activity. When stress moves through such an irregular foundation, it can cause unpredictable effects. Energy can be absorbed in one layer, then suddenly released in another, sometimes hundreds of miles away. This makes it difficult to pinpoint exactly where the next release might occur. The very fact that geologists have issued a red alert signals that they see this as not just an isolated tremor, but as the opening move in a potentially larger sequence of tectonic adjustments. One possible factor behind the movement is the interaction between deep-seated mantle currents and the crust above. The mantle is not a static, uniform layer. It flows and circulates over geological timescales, carrying heat and material from the Earth's core outward. These flows can create hot spots, areas of unusual heat and pressure that push upward on the crust. In most cases, these forces act so slowly that we never notice. However, when conditions align just right, the pressure can localize along old weaknesses in the crust, forcing them to shift suddenly. Tennessee's subsurface contains a lattice of such weaknesses, some dating back over 1 billion years to the breakup of ancient supercontinents. These hidden scars, invisible at the surface, can become the perfect pathways for deep energy to express itself. The shift has also drawn attention to the complex interplay between natural seismicity and human activity. In recent years, parts of the central and eastern United States have seen an uptick in earthquakes linked to deep wastewater injection, hydraulic fracturing, and other industrial processes that alter subsurface pressure. While there is no immediate evidence that such activities triggered this particular movement, the possibility of a contributing influence cannot be entirely ruled out. Geologists know that even a small change in the balance of forces underground can be enough to set off a chain reaction if the crust is already near its breaking point. Data from ground-based sensors revealed not only the physical movement, but also subtle changes in the Earth's magnetic field and gravity in the affected area. Such changes are rare but significant, as they indicate mass redistribution at depth. Essentially, something is shifting the density distribution of the crust and upper mantle, altering how the planet's gravitational pull interacts with the surface. These anomalies are like fingerprints, offering clues about the processes at work miles beneath our feet. Interpreting them will take time, but early readings suggest the involvement of deep crustal fluids, perhaps remnants of ancient oceans trapped in the rock, being forced into new pathways by the shifting mass. The issuance of a red alert is not done lightly in the geological community. It is a designation reserved for events with the potential for significant impact, either through direct seismic hazard or by triggering cascading effects in the surrounding region. Such alerts are designed to prompt heightened monitoring and readiness, not only from scientists, but from infrastructure managers, emergency planners, and even industries that depend on the stability of the ground. In Tennessee, a state whose lifelines include extensive road networks, river transport routes, and power generation facilities, the integrity of the ground is not an abstract concern. Any significant destabilization could ripple quickly through both the economy and daily life. From a purely scientific standpoint, the sudden crustal movement offers an invaluable, if unsettling, glimpse into the dynamic processes that shape the interior of the continent. Most of the time, the North American plate drifts sedately westward at a pace slower than fingernails grow, its motions too gradual to notice without precise instruments. Yet events like this remind us that beneath the veneer of stability, the forces of plate tectonics are always at work, sometimes expressing themselves in ways that challenge our understanding. For researchers, this is an opportunity to gather data that could improve models of intraplate seismicity, the kind of earthquakes and shifts that occur far from plate boundaries. The unique challenge of studying such events in Tennessee lies in the relative scarcity of dense seismic instrumentation compared to high-risk zones on the coasts. The central United States has fewer sensors per square mile, meaning that when something happens, scientists must work quickly to triangulate the source and characteristics of the movement. In this case, the initial detection came from a combination of regional seismographs, GPS displacement measurements, and even underground fiber optic cables whose tiny strain changes can act as improvised seismic sensors. The more data they can gather now, the better chance they have of identifying whether this was a singular event or a part of a larger sequence still unfolding. The geological history of the area provides some hints about what may be happening. Hundreds of millions of years ago, the land that is now Tennessee sat near the equator, caught in the slow dance of supercontinent assembly and breakup. It experienced the push and pull of ancient mountain-building events, volcanic eruptions, and rifting episodes that tore landmasses apart. These episodes left behind a patchwork of rock types and fault lines that, while buried today, still hold the structural weaknesses from those violent times. In essence, the crust here is not a uniform slab, but a quilt stitched together by deep-time forces. And like any quilt, the seams are the places most likely to tear under stress. Another consideration is the role of the region's karst landscapes, areas where limestone bedrock has been dissolved over millennia by groundwater, creating underground caverns and voids. While these features occur closer to the surface than the current event's focal depth, their presence can amplify surface effects if deeper movements change groundwater pathways or cause subtle shifts in overlying strata. Even a small redistribution of stress can alter the stability of such void systems, leading to sinkholes or collapses in extreme cases. The suddenness of the shift also raises questions about energy storage and release cycles in the region. If the crust beneath Tennessee can store centuries of strain without obvious warning signs, then release it in a matter of hours, it challenges some assumptions about how intraplate regions behave. Unlike plate boundary zones where frequent small quakes can relieve stress gradually, areas like Tennessee may be more prone to long intervals of silence punctuated by abrupt, significant movements. This punctuated equilibrium makes forecasting especially difficult, as the absence of frequent quakes is not necessarily a sign of safety, but could indicate a dangerous buildup of potential energy. As instruments continue to monitor the area, scientists are also paying close attention to any possible connections to nearby seismic zones. The New Madrid seismic zone to the west and the East Tennessee seismic zone to the east are both capable of generating moderate to large earthquakes, and stress changes in one area can, in theory, influence the other. The Earth's crust, while solid to us, behaves over large distances like a complex interconnected system. A shift in one part can send ripples of stress that adjust the balance elsewhere, sometimes triggering movement hundreds of miles away. The question now is whether this Tennessee event will remain isolated, or whether it will nudge other fault systems toward activity. Beneath all of this analysis lies a simple, humbling truth. The ground beneath our feet is far from static. Even in places long considered geologically quiet, the deep machinery of the planet operates continuously, reshaping and realigning the crust. Moments like this, when that machinery makes itself suddenly visible, serve as stark reminders of our place in a much larger system. We live on the skin of a restless world, and every so often that restlessness forces its way to the surface in ways that demand our attention. The Tennessee crustal movement may fade back into geological obscurity, becoming just another data point in the vast record of Earth's internal life. Or it may mark the beginning of a longer, more complex sequence of adjustments that reshapes our understanding of the region's seismic potential. For now, all that is certain is that something deep and powerful has stirred beneath the heart of the state, powerful enough to trigger the highest level of geological alert. Scientists will continue to watch, measure, and interpret, piecing together the clues from instruments scattered across the region. Each reading, each waveform, each subtle magnetic shift adds to the evolving picture of what happened and why. The scale of the crustal movement beneath Tennessee becomes even more striking when viewed in the context of how rare such concentrated seismic signals are in this part of the country. For decades, the recorded seismic activity in Tennessee has tended to register as minor, often imperceptible to the human senses, and detectable only through sensitive instruments. These small quakes, when they occur, are usually interpreted as stress readjustments along minor faults or as background seismic chatter that has little impact on surface conditions. What unfolded this time, however, was of an entirely different magnitude in terms of energy distribution and geological footprint. The red alert status was triggered not by a single jolt, but by a sustained and measurable displacement of rock layers miles beneath the surface. This prolonged nature of the event means that it was not simply the snapping of one fault, but rather a coordinated movement across a wide zone. Such synchronous deformation implies a high degree of connectivity between deep crustal structures, almost as though several hidden levers had been pulled at once in the subterranean machinery of the Earth. That kind of connectivity challenges current seismic models for the area, many of which assume that faults here are relatively isolated from one another compared to more active plate boundary regions. The Tennessee Valley's underlying geology offers some tantalizing clues to this phenomenon. In certain regions, layers of dense crystalline basement rock are overlain by softer, more ductile sedimentary deposits. When stress accumulates, these contrasting layers can respond in dramatically different ways. The rigid basement rock may fracture abruptly, while the overlying sediments may deform more gradually, transmitting strain over greater distances before breaking. In this case, the simultaneous movement suggests that both layers were involved in the shift, hinting at a complex failure mechanism that is not easily categorized. Adding to the intrigue is the role of deep fluid migration. Over millions of years, mineral-rich fluids have moved through fractures in the rock, sometimes leaving behind metallic veins, sometimes altering the chemical structure of the host rock entirely. If such fluids are mobilized by a sudden thermal pulse or by shifting pressure conditions, they can act as lubricants along fault surfaces, dramatically lowering the friction that normally keeps the rocks locked together. This reduction in friction can transform a stable fault into a rapidly slipping one, essentially flipping a switch in the Earth's mechanical system. While the data so far does not confirm the presence of such fluids during this movement, the possibility is under serious consideration by geologists studying the event. Another dimension to the movement is its possible relationship with mantle-derived stress pulses. The North American plate, though seemingly solid, is subject to slow undulations caused by variations in mantle convection beneath it. These undulations can produce cycles of uplift and subsidence over vast regions, imperceptible to humans but measurable over decades through precise satellite-based instruments. If Tennessee happens to lie in a zone experiencing a subtle phase of uplift, the added vertical stress could interact with existing horizontal compression in a way that primes faults for sudden release. The fact that the recent movement included vertical displacement supports the theory that deep vertical forces may have been a contributing factor. The broader regional tectonic picture is also relevant. The eastern half of North America is under a complex web of stresses stemming from multiple sources. The Mid-Atlantic Ridge pushing from the east, the slow collision forces from the west via the Pacific Plate's influence, and even the gravitational adjustments from melting ice sheets in the far north, a process known as glacial isostatic rebound. Each of these influences exerts only a tiny force at any given moment, but over time they can stack and interfere with one another, occasionally producing stress concentrations in seemingly random places. Tennessee may have become one of those stress focus points, and the sudden movement could be the system's way of releasing that built-up tension. While most of the attention naturally focuses on the faults and rocks beneath the state, there are also important surface-related implications tied to how seismic energy interacts with local geography. Tennessee's river valleys, floodplains, and low-lying agricultural basins are underlain by sediments that can amplify ground shaking if further seismic releases occur. This is particularly important in the Mississippi embayment region, which overlaps part of western Tennessee. Soft, water-saturated soils here could potentially magnify the effects of any shallow seismic waves that result from deeper movements. Even though the current event was centered deep underground, any shift that redistributes stress towards shallower faults would bring this risk to the forefront. The reaction from the geological community has been one of intense focus, rather than panic. A red alert does not necessarily forecast an immediate disaster, but it does signal that conditions have entered a threshold where close and continuous monitoring is essential. Field teams have begun deploying additional portable seismometers in a grid-like pattern to enhance the resolution of the seismic data. Each of these devices will capture not only vibrations from deep movements, but also the subtle aftershocks and microseismic events that often follow a major crustal adjustment. The patterns of these small events will help reveal the geometry of the faulting and the directions in which stress is migrating. The event has also sparked renewed interest in the use of non-traditional monitoring technologies. Such cables offer a vast and underused network of potential sensors. When seismic waves pass through the ground, they cause minute changes in the light traveling through the fibers, which can be measured and converted into high-resolution seismic data. This approach could allow scientists to track the ongoing changes beneath Tennessee with unprecedented detail. One of the less visible but scientifically crucial aspects of this movement involves stress shadows. Regions adjacent to a major shift where stress is temporarily reduced because nearby faults have released their strain. While this might sound like a relief, stress shadows can have complex consequences. In some areas, the reduction in stress might indeed mean a lower chance of immediate seismic activity. In others, it can create zones of imbalance that cause stress to accumulate faster in surrounding areas. The geometry of the Tennessee movement will determine where these zones form, and mapping them will be critical for anticipating possible future fault activity. Tennessee's deep crust also contains remnants of ancient mountain roots, massive blocks of buoyant, low-density rock that once supported towering peaks during the formation of the Appalachians hundreds of millions of years ago. If the recent movement intersected one of these deep mountain roots, it could have altered the way stress is transmitted through the region, setting up unusual vibration patterns that ripple far beyond the immediate zone of displacement. Some of the distant sensors have already recorded anomalies in waveforms that may hint at such interactions. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on sudden crust movement below Tennessee? What happens next? We want to hear from you. Thank you for watching, and see you next time.